Ladies and gentlemen, this class recording has started. So today, we are going to look at information related to families on the periodic table. So first, on the periodic table, we defined the term family on Friday. What does a family refer to on the periodic table? I mean, you could, pull out your outline from Friday if you can't remember. So, a family refers to what on the periodic table? Jennifer, go ahead. A column, all right? So if we go here, right, any of these columns, or if you guys want to take a look at your periodic table that's in your planner, right, any of these columns we refer to as families. We can also call them what? Groups, okay? And that is opposed to periods, right, which run which way? Left, right, the horizontal, right? They are rows on the periodic table. So today, we're going to focus on families. And most of you have noticed, and you noticed when we were coloring things yesterday, that there are certain families that down at the bottom of your periodic table have specific names, right? This group here is called the alkali metals. Group 2 are called the alkali earth metals. Group 17 are called the halogens. Group 18 are called the noble gases. And we'll introduce all of those in time, okay? But before we get started with that, like I said, I want you to take a trip to the past. Up at the top of your outline for today, you'll see that there are 6 models of atoms. First, what kinds of models are these? Bohr. These are Bohr models. Because why, Louis? What did Bohr say about location of electrons? Do you want some help? Somebody else can help you if you don't. Okay. What did Bohr say about locations of electrons? Robert? Defined shells, right? And that's what it's up here. Now, in real life, is this what a model of an atom looks like? No, it's not. But there is a reason why we still use Bohr models to help us explain certain things. And we're going to get into that today. So, the top 3 are lithium, sodium, and potassium. Here's what I would like you to do, like either above them, or you don't have much room below them, but maybe in the space above them. I would like you to write for me the electron configuration of these 3 elements. In order to help you, I pulled out this chart because you might need it, right? So, write me the electron configurations for lithium, sodium, and potassium. Yes, David?
Why isn't there any strong nuclear force?
Strong nuclear force acts on positive things to bind them together as opposed to negative things. And it actually strong nuclear force only acts over a very short distance. It's only the distance of the nucleus, so once you get outside the nucleus, you can't feel the strong nuclear force. That's why weak nuclear force acts within there too. Actually, those two have kind of been fused together. That's sort of strong nuclear force and weak nuclear force is kind of an old way of talking about it. There's really only a nuclear force, so. But it still acts over a very short distance. Once you get outside the nucleus, you can't feel it anymore. You guys can work together on this, by the way. Sorry, I actually intended for you guys to discuss this with each other. So, write for me the electron configurations of lithium, sodium, and potassium. And if you're looking up here on the board, I will bring the chart back in just a second. I'm just going to write, okay? Electron configurations for lithium, sodium, and potassium. repeat. Yes, sir. I know it's kind of blurry, but all right, 10 more seconds. All right, in case you weren't looking up on the board before, here they are. Okay? First, even if you didn't remember how to do electron configurations before I wrote them up on the board, do those look familiar? Okay? So we talked about that this is a shorthand way of showing where electrons are in orbitals around the nucleus. All right, good there? But the one thing that I really want us to notice in relation to this discussion is this, and this, and this. Okay? First, we actually gave those electrons a name a little bit earlier. You may or may not remember them. Okay? Does anybody remember what the name of those electrons are? We discussed it briefly when we were talking about electron configurations. Anybody remember what the name of those are? Those are valence electrons. Okay? Those are valence electrons because they are in the highest energy level that atom has. Okay? So valence electrons are in the highest, if we want to start adding terms from before, principal energy level. Okay? Valence electrons are electrons in the highest principal energy level. Okay? Now, more important to this discussion, how many electrons total does lithium have? How many electrons total does lithium have? 3. Okay? 1, there's 3 silver spheres on this picture, but 2, how do we find out how many electrons an atom has? Periodic table, right? So if we look at our periodic table, okay, here's lithium, top left, here's its atomic number, 3, right? So lithium has 3 electrons total, but how many valence electrons does it have? Just 1. The highest principal energy level in lithium is which energy level? 2. And how many electrons are in the second energy level? Just 1. How many electrons total does sodium have? You could look on your periodic table after all, right? Okay. Sodium has 11 total electrons, but how many valence electrons? 1. Which energy level is that electron in? The third energy level. How many electrons total does potassium have? 19. But how many valence electrons does it have? 1. Good? All right. There's a reason why I gave you these 3, right? If you find them on the periodic table, what do you see about those 3? They are in the same family. And they also have the same what? I just took you through this discussion, right? They're in the same family and they have the same number of valence electrons. Coincidence? Probably not. All right? So, next, before we get to the outline, the other 3 Bohr models that you have on your sheet. There's fluorine, there's chlorine, there's bromine. Write me electron configurations for those three. There's the chart. Work with the person next to you. Electron configurations for fluorine, chlorine, and bromine. All right, I'm going to write some electron configurations. I'll put the chart back up in a second, promise. Last one, right? Pay attention to which way the orbitals fill. All right, remember on this last one, on bromine, pay attention to which way the orbitals fill, right? That's not going to work. All right, I'm going to write this last one up on the board. Ready? Here we go. Better hurry.
I got it. I think. Oh, I got it right.
Yeah, Gustin. All right, so there are the electron configurations for fluorine, chlorine, and bromine. Let's take the discussion that we did for the first three and take it here, right? On our last discussion, we focused on which electrons in particular. The valence electrons. I kind of gave you the answer, right? Valence electrons are electrons that show up in the highest energy level, or the highest principal energy level. For fluorine, what is the highest principal energy level? 2. How many electrons are in the second energy level? There are 7. Even though this is an s orbital and this is a p, and these are p orbitals, they are all part of the second energy level. So, fluorine has how many electrons total? How many electrons total? 9, but how many valence electrons? 7. These two count, even though they are in an s orbital. Valence electrons are the highest principal energy level. Right? 2's the highest principal energy level. There are 7 electrons total. Does that make sense? Okay? Let's apply it to chlorine. Chlorine has how many electrons total? 17. How many valence electrons does chlorine have? 7. Okay? Good there? And then, and this one gets even trickier, bromine, 35 total electrons. What is the highest principal energy level? 4. But some of them are here, and some of them are here. How many valence electrons does bromine have? 7, even though the electron configuration has them broken up. So, fluorine, chlorine, bromine each have 7 valence electrons. And if you look at the periodic table, here's fluorine, here's chlorine, here's bromine. What do we see about the 3 of them? They're in the same family, same valence electrons. Coincidence? Go. Okay. All right, so that being said, let's go here. All right, as we just kind of talked about, valence electrons, I just defined them for you a little while ago. Valence electrons are electrons that are in the highest occupied energy level, or I guess probably to make this more consistent with what we discussed, highest occupied principal energy level. Okay? Valence electrons are electrons in the highest occupied principal energy level of an atom. Good there? And as we just saw, okay, so here's a Bohr model, right? Out of A, B, C, and D, which one's a valence electron? A, right? Bohr models are good for showing valence electrons. They don't show s orbitals and p orbitals, but they do show electrons in the highest energy level. That's why we still use Bohr models, because valence electrons are important to understand element behavior, right? So A is a valence electron. It's in the highest occupied energy level. But, more importantly, these electrons are important when we talk about how atoms react with other atoms. And that's what we call chemical reactions. We will spend the next couple units talking about how chemical reactions occur and then why they occur. All right, that's where we head a little bit later on in this course. Okay? Atoms are trying to get to 8 valence electrons. Why? It's a low energy state. And remember, we discussed a lot when we were talking about the location of electrons. In nature, things try to get to low energy states, right? We talked about this 100 times, right? If I let go of the ball, it falls to the ground. Why? No, not because of gravity. Gravity is how it happens. Why does it happen? It loses, more importantly, the potential energy, right? Low energy states. 8 valence electrons is a low energy state. Okay? Atoms want to be in low energy states, and they will do what they can to get there. That determines a lot about how atoms behave. All right? If every single atom in a family has the same number of valence electrons, they all have to do the same thing to get to 8 valence electrons. Does that make sense? If we go back to these 3, how many valence electrons did we say each of them has? 7. So to get to 8, what do they have to do? They have to pick something up somewhere, right? They have to pick one more up. This one will pick up 1 electron. This one will pick up 1 electron. This one will pick up 1 electron. And that means they all behave similarly. Does that make sense? Because they're all trying to accomplish the same goal. Okay? And that plays a big role in determining element behavior. Okay? So, The first group of elements that we come across is group 1. Okay, Johnny, go ahead. Oh. So, elements in the same family have similar properties because they have a, or blank, of valence electrons. Same number of valence electrons. Sorry. That's actually this page right here that kind of shows how the pattern goes. Okay. All the elements in the same family have the same number of valence electrons. There it is. All right, good there? So let's start talking about some of those valence electrons, or some of those families. The first family we come across is group 1, which means it's going to be where on the periodic table? Column 1, right? Very, very far left. That group we call the alkali metals. And, just like we discussed, they all have similar properties. First, they are all metallic. Remember when we colored in our periodic table on Friday? Metals show up on which side of the periodic table? Left. These elements are the most metallic you can get. Okay? They are very soft, which I know we don't think of generally as a metal, but that actually is what makes something metallic, or one of the reasons that or one of the properties of a metallic substance. Okay? What we call metal commonly in the real world doesn't always match up with the description of metallic from a chemical perspective. Okay? They are very shiny, but they will react with a lot of things, specifically oxygen in the air and water. Why? Because they have one valence electron. Now, I told you that the magic number was what? 8. So you might think, well, wait a second. Something that has one valence electron isn't very close to having 8. But what we will find when we talk about chemical bonding is that there are two ways that atoms can get to 8. They can either pick up electrons and go up to 8, or they can lose electrons and go down to 8. For example, here's, nope, not chlorine. Here's sodium. Said sodium, the highest energy level that it has currently is the 3rd energy level, but it only has 1 electron in it. We could pick up 7 more electrons in that outside ring to take the outside ring up to 8. Or, if we just get rid of this one, right, and go from 11 down to 10, okay, it won't match up the number of electrons and protons. Fine. But if we lost that electron, now what's the highest energy level that sodium has? It goes from being the 3rd energy level to the 2nd energy level. And how many electrons are in that 2nd energy level? I'll give you a hint. Well, no, not 10. It has 10 total, but 2 of them are in this first ring, and that means how many are in the 2nd ring, Polly? 8. And then that's where we want to be. Okay? So, elements that have 1 valence electron, even though that's really far from being 8 by gaining electrons, they can lose electrons and get down to 8 pretty quickly. So 1 valence electron is actually very reactive. Go ahead, Donna. To them, losing electrons is losing potential energy, right? That's how that atom loses, that atom gets to a lower energy state, okay? But, and this is kind of previewing a unit from now, all right? So sodium has 1 valence electron. If it loses that valence electron, the third energy level goes away, and now the second energy level is totally full with 8. Yes? All right. Here's chlorine. Chlorine has how many valence electrons? 7. So it could, in theory, lose all 7 of these valence electrons. And then that would leave the second ring totally full. Or it could do what? It could pick up 1 to fill up the third ring. Okay? Sodium is looking to do what with its 1 valence electron? Well, it's looking to lose it somehow. Chlorine's looking to do what? Gain it, right? That happens, and you know what you end up with? NaCl. Ever hear of it? That's table salts, okay? So that's how we make new compounds, is that these individual atoms are looking to either get rid or gain electrons, so they sort of trade with each other so that everybody's happy, but in the process that joins them together, and that's what we call a compound, right? So sodium is an alkali metal in the first family, okay? It has 1 valence electron. Chlorine is in another family and has 7 valence electrons, but they join together to make table salt. Prediction time. What other elements might join together with chlorine? Discuss with the person next to you. What other elements might join together with chlorine? I was going to bring that up today. The last test that we took when you guys were spreading around the room, that bag was left back in the paper bag full of syrup. I don't know why. So that's why. All right. So, anyone care to make a bold prediction? Rocco, go ahead. Rocco says potassium is another element that is likely to join with chlorine. That is a correct answer. Rocco, why is potassium likely to join with chlorine? Okay, potassium chloride is an element. Let's talk about why. Peyton, go ahead. Oh, you were just cleaning out your eye? Okay. Charlotte, good. Okay, going back to our electron configurations, right? How many valence electrons does potassium have? 1. What do things with 1 valence electron look to do? Get rid of them. How many valence electrons does chlorine have? 7, right? What's it looking to do? Gain 1. Elements in the same family behave similarly because of their valence electrons. Okay? Hold on 1 second. Let me make one prediction. Okay. I want you now talk to the person next to you. What are 2 elements that we haven't discussed yet that you might feel likely to join together? Okay? Discuss. Go. It does it a different way. Whereas sodium and potassium just give that electron away to chlorine. Hydrogen sort of shares that electron with chlorine. Okay, that's a story for another unit. Okay. All right, are we ready? 2 elements that we haven't discussed previously that you might predict would be likely to join together. You answer the last question. Sorry, Charlotte. Not that I don't want you to. I just don't want you to dominate the conversation. So, all right, 2 elements that we haven't discussed previously that you might predict would join together? Well, the whole purpose of this discussion starts... Eric, do you want to take a guess or do you want me to finish my statement? Okay, the whole purpose of this discussion starts off with the fact that what determines the behavior of atoms? The number of valence electrons. And what do we know about the valence electrons of elements in the same family? They're the same. So, give me a prediction about which two elements you might think would join together. Eric? Let's stick with same families at this point in time, because that's the point I'm trying to make, all right? Okay. Okay, so Eric says cesium, okay, which is here, and iodine, which is here. Why? Because elements in the same family behave similarly. Cesium will behave the same way as potassium and sodium do. Iodine will behave the same way chlorine does. Why? Because they have the same what? Valence electrons. All right, good there? At least for our discussion, for starters? Okay, Peyton, go ahead.
Okay, so 8 is like the number taken because of stable effect.
Yes. Do you want to take that any further, or are you just clarifying?
And then, no, like what happens if it's anything over 8?
So, the thing is, right? So that was a good question. Peyton said, just for the sake of recording, right? Peyton said that 8's like the magic number. It's the stable number, okay? She said, what happens if anything gets over 8? And the answer is, you can't go over 8. Because here, let's go back to these pictures. Okay. Here's sodium, right? Actually, let's go here. Okay. 2s will hold how many electrons? 2. 2p will hold how many electrons? 6. So a total now of how many? 8, right? But once you fill this up, where do you go next?
Oh, yeah.
Then you go to 3. Then you go to 3p, right? Now, when you get here in D's and F's, things start getting weird. Because remember, you have all kinds of like mixing like going on here. Does that sound familiar from, like, remember we talked about how because you get a much bigger space, some of those orbitals, even though they might be in the 3rd energy level, might actually be farther away from the nucleus than the 4th energy level because you just have lots more space for them to fill, okay? We're going to stick, at this point, with S's and P's, right? So that means that for now, Peyton, we're not going to discuss any of these elements that are in this section right here, okay? And if you're talking just S and P, the most you can have is 8, because once you fill up all the P's, then you go to the next energy level, okay? So that makes sense? Yeah, so the answer is you can't have over 8, because once you get to 8, you go up to the next level, and then you start over the process again, okay? All right, let's finish this outline. We've actually hit a lot of things that are in this outline already. So, let's jump ahead to the back side, and let's talk about group 17, of which fluorine, chlorine, and bromine are all a part of. All right? So we call group 17 the halogens. Whereas all of our alkali metals are solids, halogens have much more variance in their properties. Some are gases, like fluorine and chlorine. Bromine is actually a liquid at room temperature, and iodine is a solid. But they do have one thing in common. They all have 7 valence electrons, and that means they're all looking to pick up 1. And that makes them very reactive, especially with the alkali metals. Why? Because alkali metals, column 1, have 1 valence electron, and they're looking to get rid of it. Halogens have 7 valence electrons, and they're looking to get to what? 8. So if one atom is looking to give up 1 electron, and another atom is looking to pick up an electron, guess what they do? They trade nice and easy. Okay? All right, good there. But group 17 on the periodic table, right, far right-hand side, has how many valence electrons? All the ones in group 17 have how many valence electrons? 7. If you move one more square to the right, let's say chlorine, right? Chlorine has 17 electrons and has 7 valence electrons. If you move one more square to the right, that's 18 electrons, and that will give them how many valence electrons? 8. So Peyton, we said that's the magic number, right? Group 18 we call the noble gases, or sometimes we'll call them the inert gases. Okay? We call them that because they don't really do anything. They don't join together with other atoms at all. Why? Because they already have how many valence electrons? 8. Do they need to gain or lose anymore? No, so they're kind of snooty about it. And they're like, I don't need to get any electrons from you. You don't need to get any electrons from me, so how about if I go my way and you go your way and we're good, right? The inert gases, right? Or if we talk about it from the standpoint of the noble gases, right? Because if you guys like talk about like medieval times, right? The noble people don't deal with anybody else, right? You know what I'm saying? That's what these are like. Okay? Donnie, go ahead. Yep. Okay. So that's a good question. Donna said if they have 8 valence electrons, what's up with helium? Why is it in that why is it in that column? Helium has how many electrons, Donna? 2. But those electrons both go in which orbital? Specifically 1s, right? But are there any other orbitals in the first energy level? Is there a 1p or a 1d? No. So the first energy level is full even though it only has 2 electrons. Does that make sense? And so that's why helium behaves the same way. Not so much because it has 8 valence electrons, but because its energy level is totally full. Does that make sense? So it's a low energy state even though it only has 2, just because it doesn't have much room to fill. Okay? Good there? Okay. Let's talk about a couple other families that we passed along the way, all right, or that we passed one along the way. The alkaline earth metals, okay? The alkaline earth metals are similar to the alkaline metals in that they are reactive, but they're not quite as reactive as the alkaline metals, because alkaline metals only have to give away how many valence electrons? 1. But alkaline earth metals have to give away 2 valence electrons. And that's a little bit harder. And that means that they are less reactive, but still pretty reactive. Okay? Good there? We did halogens, we did noble gases. All right. Let's talk about hydrogen. Okay? Hydrogen's kind of on its own. It's a little weird because it only has 1 electron. That means it can go a couple of different directions. So, can hydrogen gain 1 electron? Well, let's talk about this. How many valence electrons does hydrogen have? 1. It's only got 1 electron, so it only can have 1 valence electron. Okay? Can it gain an electron to fill up the 1s orbital? Yeah, it can. Okay? But if it loses an electron, it can also kind of do that too. Alright? So hydrogen's kind of on its own. And that means it will react with lots of things. It can react with metals. It can react with non-metals. We'll usually find that that's not the case. Usually elements will react with one or the other, but not both. Hydrogen is not like that because it has that one specific valence, just that 1 valence electron. Okay? Good there? I'm trying to remember what else I have on here. What's the next one? Oh, transition metals, right? Okay, so transition elements. Transition elements are metals. That means they are reactive, but not quite as reactive as alkali metals or alkali earth metals. Okay? Because of the d orbitals, it gets confusing sometimes as to what's a valence electron and what's not a valence electron. So you will find that a lot of transition elements actually can accomplish lower energy states in a couple different ways. Okay. If you look at the electron configurations of all of these elements, they all end in the D sublevel, either 3D, 4D, 5D, or 6D. So we sometimes refer to that part of the periodic table as the D block, because all the electron configurations are Ds. But what that means, just like I kind of described to you before, is that because there's lots of sort of mixing of orbitals and D's and P's are kind of different levels because there's so much room there, there's a lot of weirdness that goes on in the transition elements section. And what that means is, the bottom bullet says, you can have the same element that behaves differently depending on what situation or what other elements are available to it. So you can have the same element, but it can have a different charge depending on what it's joined together with, and that will give it different properties. So, moral of this story is, when we talk about bonding, we talk about atoms joining together to get to lower energy states, we're going to completely disregard transition elements because it's hard to find patterns in there. Okay? And then lastly, we have our F block elements, which are the very bottom of the periodic table, those two rows at the bottom, or the inner transition elements. Okay? A lot of them are reactive, okay? But a lot of them, especially the ones in the bottom row, are radioactive and don't occur naturally here on Earth or anywhere in the universe for that matter. We kind of make them in a laboratory, and so a lot of times we don't make compounds out of them because they're not real. So. All right. Last thing before we take off. Okay? So, calcium. Find calcium on the periodic table. See how well we've taken in everything today. All right. Calcium on the periodic table. I would like you to discuss with the person next to you. What is one element that calcium might be likely to join together with? Discuss with the person next to you. One element that calcium likely to join together with. Don't kid. No, don't kid. That's a good answer. What did you say? That's a good answer. Can you explain why?
Well, I just didn't say it because number, it's top number above, and it was like the best.
No, that oxygen is a good answer. You just have to explain why.
I like the answer.
All right, let's discuss. So, first, calcium belongs to which family? We introduced it a little bit earlier in the period. The alkaline earth metals. But more importantly for this discussion, how many valence electrons does calcium have? 2. Okay? Because it's in the family that every other element has 2 valence electrons. Okay? So, Peyton, can I use your example? Okay, so in the course of the discussion, Peyton yelled out oxygen. Okay? Although she wasn't sure why, she was just kind of throwing it out there. But oxygen actually is a good answer to this question. Calcium has 2 valence electrons. What is it looking to do with those 2 valence electrons? Get rid of them. Okay? To get down to 8. Okay? So it needs something that has how many valence electrons? 6. Okay? Okay, good.
So as soon as like you hit 0, they still need 8?
0 and 8 are kind of the same thing. Okay? So, yep.
218, 7.
So, Peyton, with that in mind, here's the halogens, right? How many valence electrons did we say halogens have? How many valence electrons does halogens have? 7. So if you go one more to the left, how many valence electrons will oxygen have? 6. That means that it needs to gain how many? 2. Guess where it gets them from, or could get them from? Calcium, is it looking to get rid of its 2. Okay? All right. Good job today, everybody. Lots of good connections and things like that. There is some homework on the calendar for tonight. It's reading some pages on this section and answering a couple of questions about properties of elements.